going. So I'm going to stream the natural number game, and I should perhaps do that. Hello. I should perhaps start by going to yeah. I'm going to reset my progress, and now let's go to the tutorial. So I talked to my children are two teenage boys aged 18 and 20, and they complain that the big problem with the natural number game is there's far too many words. So let's not read any of the words. Let's just start here, and I'll tell you what the words say. So if there's anyone who's never played the natural number game before, then I think the first thing you need to learn is that, so what's going on here is we're trying to prove, look, we're trying to prove a little maths puzzle, right? Here's a lemma. Oh, it'd be nice if I could see. I can't see what's happening. Oh, I've had this problem before. So here's a lemma, and that lemma's called example 1, and the lemma says that x times y add z is x times y add z. So pretty clearly that's true, but our problem is that, look here, we've got to prove it, right? So here our job is to construct a proof of this lemma there, and as any professional mathematician will tell you, the reason this lemma is true because equality is a reflexive relation, right? Equality is a reflexive binary relation there. So we have to figure out how to make this crazy system so that equality is a reflexive binary relation, and the way that's done, reflexivity of equality, is abbreviated in the system to REFL. So if I type REFL here, then it says proof complete. So what just happened there is we've proved a theorem. So before here, the goal was x times y add z equals x times y add z, which is obvious. It's trivial. Does that work? I bet trivial doesn't work. Trivial is a proof of true. Oh, trivial. Oh, the trivial tactic. Is that right? Oh, the trivial term is a proof of 2. Okay, great. I don't know what this tactic does. Let's go to lean prover. Let's just Google for mathlib. Let's Google for mathlib. Let me just check out that. I'm confused now because I don't know what this tactic is. And there's the thing I'm after. The lean prover community website, and then I can look at the API documentation. Let's take a look at the tactics. There's a tactic called trivial. Here's trivial. Tries to solve the current goal using canonical proof of true. Oh, there you go. So it either produces the canonical proof of true, or it uses REFL. So trivial is just REFL plus plus or something. Right, let's leave those tactics there. There you go, REFL. So that's why that goal is true. Right, let's press on. So level 2, we have to do something, right? Because here, REFL doesn't work here, right? Because REFL only works when the two sides are equal by definition, and there's a problem here. So x, what's going on here is that x and y, what does that mean? X, y, minor. That means x and y natural numbers, and h, y equals x plus 7. I'm looking at I can't see if you can see what I'm highlighting. Can you? There you go. Can you see? Is everything orange? I can't see what I'm streaming. Oh, I can see what I'm streaming. Yeah. Everything is grey. Great. Ooh. Is there some switch from red to blue that I need to do? Wait a second. Is everything the wrong colour? Swap red and blue. No, I can't. It looks orange to me, but it looks grey to you. Hard luck. So all that stuff that's grey, oh, there you go, it is orange. All that stuff that's orange, there, no, wait, this stuff here, all that stuff that's orange, that says x and y are natural numbers, and that says h is a hypothesis that y equals x plus 7, and we're trying to prove that 2y equals 2x plus 7. So the way we need to do that, right, the problem, we need to sub in, right? Sub in. And all that stuff here, oh, there you go, it's not that big. This tutorial level tells you that the way to do substitution is the rewrite tactic. So we can do rewrite h there, and that replaces the left-hand side of h with the right-hand side. So what's going on here is that we have a goal, right? And our goal at the beginning is to prove that 2 times y is 2 times x plus 7, and our hypothesis is that y is x plus 7. So when we rewrite h, it replaces this y with x plus 7, and you can see that the goal becomes 2 times x plus 7 equals 2 times x plus 7. So we can solve it by reflexivity. So there you go. Those of you that have played some other levels of this might know about the cases tactic. So let me show you another proof. Another way of substituting it is I can do the case. Look, I can do cases h, because equality is an inductive type. That completely messes up everything. So there you go. Everything has become completely incomprehensible. But in fact, I think REFL will still solve this. So there you go. So there's a rather exotic proof. There's a rather exotic proof of that level. But perhaps, I mean, yeah. The reason cases works is that if you've got a proof of A equals B, then the only possible case is that A has to equal A. So, I mean, that's not the proof that I'm recommending in this game. I'm recommending this proof. Rewrite H. And then REFL. There we go. So rewrite is short for rewrite. I should say, the natural number game, I hacked the rewrite tactic. If you did this in lean, then after the rewrite, the goal would just close instantly anyway, because after a rewrite in lean tries REFL anyway. But I hacked the RW tactic, but I never hacked the full rewrite tactic. So if I do rewrite H here, then we don't have to do the REFL either. So there you go. So there's another proof of that tutorial level. Let's press on, because it would be nice if I could finish Power World. Blah, 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 blah. Let's not read all that, because let's pretend that we're 17 and we can't be bothered to read. So what's going on here? Let's just look at what's going on up here. So we've got two natural numbers. Oh, we've got this suck. So maybe I should tell you that Peano's axioms, have we got Peano's axioms up here? Great. Peano's axioms say that 0 is a natural number, and they say the successor of a natural number is a natural number, and that's it. And so this suck means the number after. So what's this lemma here? I see the lemma says if the number after A is B, then the number after A is the number after B. And again, how are we going to prove that? We're going to prove that by we can just, yeah, so we sub in again, don't we? We could sub in either direction. We could do rewrite. If we do rewrite H, then the goal becomes suck B equals suck B, which is true by reflexivity of equality. So REFL. There. We could probably also do rewrite. If I put that little arrow there the other way, rewrite H the other way, the goal now becomes, you see, now the goal is suck A equals suck A. So we could also prove that by REFL. So we can either substitute in for B or substitute in for suck A. And we could probably do cases on it as well. What happens if we do cases? Cases H. Oh, there you go. Then suck A is suck A. So there's some proofs of that. Can I do induction H? There you go. There's a proof. There's a proof by induction on equality. So there's some proofs of that. Let's go on. Oh, finally we have addition. Okay. So I should maybe open up. Look, these little drop-down boxes on the left here. They tell me that we can learn about the REFL tactic and the rewrite tactic, but we should also learn about what theorem statements we have. So here, what's going on? So we're trying to prove things about Peano's natural numbers. That's the goal of this game. So A is a natural number in the sense of Peano. So 0 is a natural number, and the successor of a natural number is a natural number. And this is what we've got to prove. We've got to prove that A add the... So the successor of 0 is 1, obviously. So we've got to prove that A add 1 is the number after A. And this has been a carefully designed level, because what I've just explained in all this waffle up here is that we've added two axioms to the system. And the first axiom is that A add 0 is A. And the second axiom is that A add the number after D is the number after A add D. So those are the two axioms we've added. And so let's rewrite using those axioms. How are we going to prove this? A add the number. What have we got? You see, we have a theorem about A add the number after something. So let's rewrite add suck. There. And now our goal has become the successor of A add 0 is the successor of A. So here we have A add 0, and we have a theorem about A add 0. Add 0 is the theorem that A add 0 is A. So we can rewrite add 0 there. And now the goal has become suck A equals suck A. So this goal here we can solve by reflexivity. right? What does reflexivity mean? Both sides, you know, left-hand side equals the right-hand side by definition, right? That's the kind of goal that REFL will solve. The left-hand side equals the right-hand side by definition. But actually, this thing here, this add 0, this is part of the definition of addition, you see. So add 0 is actually true by definition, right? This is true by definition. And add 0 and add suck. These are both the definitions of addition. So these are both true by definition there. And so in fact, when you think about it, I claim that in fact, you know, what is the definition? What is the definition of the left-hand side, right? The definition of the left-hand side is a. I'm just going to, you know, a plus suck 0 is defined to mean suck of a plus 0 there, and that's defined to mean suck of a, right? Because these things here, a add 0 is a, and a add suck b is suck of a add b. These are true by definition. So the left-hand side is suck a by definition, and so is the right-hand side. So I think that means that I can just solve this goal by REFL anyway. You see there? So that's quite a surprising for people that have played this game but don't know anything about definitional equality. I think that this is a surprising proof, right? There, a plus suck 0 is suck a, because I'm encouraging people to solve this by doing some rewrites, but in fact you don't have to do the rewrites because the rewrites are definitionally true. So I don't think there's anything else of relevance here. So now let's finally, there we go, we've unlocked addition world. So let's go to addition world. So here we are at addition world. And addition world, we've got to prove that 0 plus 0 is n. Sorry, 0 plus n is n. And so you might kind of think, well, let's unfold these things here. Let's look at what's known in addition world. Remember, a plus 0 is a. That's true by definition, right? Recall that a plus 0 is a is true by definition, right? I can show you this. Like I can. Oh, it's called n now. Let's call it n. N plus 0 is n is true by definition. We could even do this. We could do have h. We could do have h n plus 0 equals n. There. There. And now you see we've got an extra goal. N plus. You see now we've got two goals. Now we've got to prove that n plus 0 is n, and we've got to prove that 0 plus n is n. And this thing is true by definition. There. So n plus 0 is n is true by definition. But now what about this 0 plus n is n? Let's try REFL here. And now this fails, you see, invalid there. I have some error, right? I have an error there. So 0 plus n is n is not true by definition. So what do we learn? As a mathematician, what do we learn from this? What we learn from this, does REFL work on add 0? Yeah, add 0 is just true by definition. Yeah, you can prove add 0 by REFL, absolutely. Yeah, it's one of the secrets of the natural number game. But 0 plus n is not true by definition, and the conclusion is that what's true by definition is of no relevance. I mean, definitional equality is somehow not mathematical, right? Not a mathematical concept. Because if you ask just a regular mathematician, I'm going to put sorry to get rid of this error. It's annoying that I've got an error. There, great. Things are now good, except I've cheated. So n plus 0 is n is true by definition. 0 plus n is n is not true by definition. So what's going on is that definitional equality can't somehow be the way a mathematician thinks about equality, right? So somehow equality, mathematicians think about it. To a mathematician, there's no difference, right? Both n plus 0 is n and 0 plus n is n. Both of those things are true by definition in a mathematician's mind, or they're both obviously true, or they're true because the natural numbers are a monoid under addition or something. Well, you know, whatever reason. I mean, that's the point. We're trying to prove that the natural numbers are a monoid under addition at this point, you see. So definitional equality is a slightly weird thing. So how are we going to prove this? We have to prove this by induction, right? Induction n with DHD. there. So now we have two goals. When you try to prove things by induction, we have a base case and we have an inductive step. So let's, I'm going to try and do proper programming practice here. So because I've got induction, I've put some braces. And so you see just in the first goal there, we've got to prove that 0 plus 0 is 0. And in the second goal there, we have the hypothesis that 0 plus d is d. And we need to prove that 0 add the number after d is the number after d. So in this one here, why is that true? Well, you see, I guess you could do rewrite add 0 there, and then that becomes 0 is 0, and then you could prove this by REFL there, and then this line can go. So that would be somehow the officially sanctioned proof. But because add 0 is true by definition, you don't have to write that. We can just delete that there. Oops. There. So 0 plus 0 equals 0, you can prove by REFL. In fact, equality of any two natural numbers you can prove by REFL, right? I should maybe look. Oh, yeah. Look at this, look. Have h, 2 plus 2 is 4. There. And now we'll have see, now we've got a new goal to prove that 2 add 2 is 4. And that's going to be proved by REFL. So there you go. I go around giving talks at schools showing this proof of REFL. And then I claim that REFL is an incredibly powerful tactic. I mean, which in some sense it is. But it's also just reflexivity of equality. But it's reflexivity of definitional equality. That's the funny thing. So, right, what's going on? You see, I didn't know anything about tactics when I wrote this game. I didn't know anything about simp, rather, when I knew about rewrite, but I didn't understand simp. So the way you're supposed to prove this in the natural number game, we've got plus suck, right? We've got add successor, so we can rewrite add suck there. And now the goal is suck of 0 plus d is suck of d, and 0 plus d we know what it is, right? 0 plus d isn't d by definition. HD isn't true. HD isn't true by definition. HD is a theorem, right? HD is a proof. 0 plus d equals d is a theorem, and HD is its proof. So we can rewrite HD there. And now we've got to prove that suck of d is suck of d, so we can prove that by REFL. But before I go on, I'm going to try tidying this proof up a bit, because instead of doing all these rewrites, we could try using the simplifier, right? So we could try this. We could do simp add suck and HD, and not actually tell Lean how to solve this level, but just say you see it works. I've got no errors down here. This area here in the bottom right is where the errors are. And here we have no goals, and probably if I hit return, I'll get, there we go, I've just got the tick. So I've just solved this level, but I haven't, I've used the simplifier. Instead of doing all the rewrites, I've told the simplifier to try and guess where all the rewrites are. So in fact, if I put star here, I could probably even do something like this. I think I can get the simplifier to prove both goals at once. If I put a semicolon here, then the next tactic will work on both goals at once. Does that prove it? No. Oh, I see. I need to tell it add 0 as well. There. You see, so this is why this game is poorly designed, right? Because the simplifier should already know about add suck and add 0, but unfortunately it doesn't, and so you have to do simp add suck add 0. So we can fix this, right? So let me show you a hack. So if we sorry this, then we can put end, right? And then exit. And now we've actually exited this proof of this lemma, and now look, and now we're in tactic mode. No, sorry, now we're in term mode. And that was something that I didn't know you could do in the natural number game. We've sort of broken out of the tactic mode shell, to my amusement. So now, once we're out of the tactic mode shell, we can fix this up, right? We can do attribute simp. Attribute simp. What am I attributing simp? Oh, add 0 and add suck. There. So now they have been tagged with the simp attributes, and now we can go back into tactic mode. What are we trying to prove? We're trying to prove this. there. Oh, it's not going to like that because we have a lemma called 0add already, so 0add primed. So now begin natural number game. There. So now we've fixed the exactly, agent escaped. We've fixed up the issue about add 0 and add suck being not tagged with the simplifier. So now I suspect that I can just delete these. I can probably now just do simp star. There, you see, so there you go. So there's another proof. So yeah, having hacked the simplifier, we can now give a simpler proof. Why does it say no goals? Oh, it's because it's completely confused about this. What if I do this? Do I get proof complete? Lean's busy. No, it's not happy. It's because I've cheated, because I put sorry. Hard luck. So anyway, we proved it, so we can just move on anyway. Unfortunately, I suspect that simplifier, I suspect that tag won't last. I think it imports the official version. What have I got to do now? So I've got to prove associativity of addition. A plus B plus C is A plus B plus C. It really feels like, you know, if you're a mathematician, you're just like, well, obviously that's going to be true by definition or something. But it's not. I guess we need to prove it by induction. Induction C with DHD. At some point, it doesn't matter what variable you do induction on. But at the minute, because we only have theorems about, most of our theorems are about what's happening on the right. We've got add suck, but we don't have suck add, you see. And so it's always best to do induction on the rightmost thing at this point. So induction C with DHD, you see if I do simp now, Lean is busy. Yeah, so it doesn't know it. It doesn't survive. I need to tell it, if I tell it to use add 0 there, then yeah, that solves it there, and then simp add suck or something. HD. How about that? So you see, no goals. Do I get? I want to get. Darn it! Where's my? Right, there's my proof complete. I need proof complete because otherwise I don't get the tick up here. You see, and I've got to do the ticks. Did I get all the ticks? Because I'm doing silly proofs. I'm slightly scared about my ticks. Have I got the ticks? Yeah, I've got the ticks. Did I get the tick for that one? Yeah, we're all good. So here we are, suck add. So what's my theorem? I've lost my theorem statements. I've got, how am I going to prove suck add? Is that true by definition? Let's try it. No, unfortunately, it's not true by definition. We have an error trying to prove it by definition. So what am I going to do? Do I need to do induction? Probably. Yes, I'm going to need to do induction. Induction B, I guess. Induction B with DHD. There. And now let's see what we've got. This first goal, suck A add 0. Oh, now this might be true by definition. Because A add 0 is definitionally equal to A. Yeah, both sides are suck A by definition. So I can prove this by REFL. There. And this one here, this goal here, what do I need? I probably need add suck. So I should maybe do simp, add suck, and HD. Will that do it? The tension. Yes, great. I've got proof complete. So there you go. What I encourage people to do, in this game is not that. No. What I encourage people to do is rewrite. Curses. Let's put that down there. What I encourage to do is like rewrite add suck. And now what have I got? And now you see I've got HD is in here, so then rewrite HD. There. And then is this true by? Are we there yet? This is short. Oh, I see. I'm supposed to now write. Oh, I see. I rewrite add suck again. There, and then REFL. But you see, I won't need that add suck because already at this point these things were true by definition. But I can't do it here reflexivity fails here. I get an error if I try reflexivity here because HD isn't true by definition. You see, you have to get that HD in there somehow. Why do I have a? What's the with that? Oh, I've put 2 commas. Happy now? You're happy. Great. A plus B is B plus A. Now, do I need induction for this? Yes, I do. So, induction B with DHD. And now, I just want to use the simplifier, don't I? Let's try simp, add 0, add suck, 0 add, 0 suck. What do you reckon? It's oh, that's because I'm talking nonsense. Add 0, add suck, 0 add, suck add, of course, is what I mean. Let's try that. Just tell it to use all the theorems. Oh, it didn't work. Ah, I see. And you see, it did. It didn't work because I've managed to reduce the question to proving A plus D is D plus A. And we have a hypothesis that A plus D is D plus A. So I should also tell the simplifier to use all the hypotheses. And now it works. But I don't get a tick. I have to hit enter. There we go. I've got my tick. In fact, that's quite a powerful. Let me. That's using everything, right? I'm going to copy that. What's the next level? Oh, suck n is n plus 1. Oh, this is. I mean, Mehmet was asking about REFL before. I think suck n is n plus 1. What do we know? So let's. I think this one is going to be true by REFL. Let's have a look at this, right? Let's rewrite 1x suck 0. There. And so that's true by definition. That's the definition of 1, is that it sucks 0. And if I rewrite add suck, then I get suck of n plus 0. And if I rewrite add 0, then I get suck n is suck n. So all of those things are all true by definition. So I don't need to do any of them. I can just do REFL will close this goal, right? There you go. There's the simplest possible proof of suck ek add 1. And now this one, I just want to paste there. Let's try this. And come on, Lean. Yeah, there you go. So you see, the simplifier is sufficiently smart. The simplifier is sufficiently smart that if I do induction and then I use the simplifier with every single thing we've proved so far, then it manages to prove it. And it would be interesting if I tried to, maybe I got lucky. If I did induction on C, would that still work? Yeah, that works as well. But if I try to do induction on A, then even though we probably have enough machinery to do it, yeah, you see, it's not so smart. Ah, it's close though. If I do induction on A, then apparently we just have to prove that B plus C is C plus B. I mean, goodness knows how Lena's managed to get to that. But if I put add com in here, I think this is dangerous. Because add com is not a great simp lemma. Does this work? Yeah, you see, look, the moment you tell Lean to use commutativity of addition, it starts going crazy. So maybe we could do this. We could do that, and then we could do it again. Try. Oh, let's just do simp. Let's try it on its own. There you go. So there's some spectacularly bad Lean code. But will it work? It works. No goals. And hence, oh, I was hoping for a proof complete. Oh, there it is, proof complete. So what we've actually done here is we proved that mynat is an adcom monoid. So I can probably escape there, and so now instance adcom monoid. What can I do? Instance adcom monoid mynat. There, by apply instance. Oh, there is a chance that this won't work because somehow, let's try. Lean is busy. Oh no, it's somehow okay. So I unfortunately I add the instance underneath where I add the instance. Yeah, I add the instance here, and so we can't play with the instance. Okay, so let's just leave it alone. So where now? Oh, we can now go left or right. I could have a vote. Let's go left. Let's go to multiplication world because I could. Yeah, why not? Let's see if I can. What's the time? Great. Let's see if I can power through this. Golly, there's 9 levels. So what's the story in multiplication world? We know that mul 0 is true by definition, but the 0 mul probably isn't. Let's try that. Refl. So that's not true by definition. So I guess we're going to have to do induction. Induction m. Induction n. Yeah, induction n with DHD. And now the first goal is true by refl. I said I'll do it properly. Look, I'm writing proper code. Look, I'm doing it like a proper computer scientist. There. And now I know that 0 times d is 0, and I've got to prove that 0 times suck d is 0. So I know I guess it's simp mul suck or something. And HD. Gosh, this thing always so. I'm so used to. So there you go. It works. I'm so used to using VS Code. This is so much slower running it locally. Maybe I should actually. Why don't I free up some memory? Here we go. Right. So now what? Oh, mul1. Oh, mul1. This is quite interesting. You might imagine. So, yeah, look at this. Mul 0 is true by definition, right? Okay, so maybe mul 1 is 2. So let's try proving it with refl. And refl fails. We have an error down here. So this is so it's not true. So it fails, right? Refl fails. So what does m times 1 is m? What does m times 1 is m actually say? Right? I don't think it's at all obvious, especially to a mathematician. I don't think it's at all obvious to see what this actually says. So let's unfold. Let's go. Let's see what these definitions are. So I guess we could rewrite 1x suck 0. There. And now we can see that really the goal is m times suck of 0 is m. And mul suck we have, right? Mul suck is the thing. So this is true by definition. True by definition. And now if I rewrite mul suck, this is also true by definition, right? There. And so now you can see that the goal is m times 0 plus m is m. And my cat's hassling me. I haven't fed my cat. Well, you're going to have to wait, I'm afraid. And now mul 0, I guess mul 0 is also true by definition. Rewrite mul 0. That's true by definition. Oh, I forgot the comma. Don't forget the comma. This is true by definition. There. So, and now you can see. And now you can see that in fact, the goal we started off with m times 1, and now we've got 0 plus m. So now we can see what's actually happened, you see. And what's happened is that 0 plus m is not true by definition, right? There. And in fact, I guess, why is that true? That's exact 0 add m, isn't it? There. So all of those things were true by definition. Oh, let's get the tick. So we can kill all of this stuff here. There. So I think this is my favourite proof. My favourite proof of mul 1. There. You can prove mul 1 by using mul 1 and 0 add are the same statement, right? They're the same definition, which is quite surprising. I guess I can show if I there, like example, if m is a minat, m times 1 equals 0 plus m, begin, end, there. So why is m times 1 equal to 0 plus m? And I'm going to put refl. Oh, I've got crazy errors down here. Let's do this. There we go. So you can see m times 1 is 0 plus m. That's true by definition, it turns out. This is just more indication that what's true by definition is not mathematically important. M times 1 isn't equal to m by definition, or m plus 0, but it is equal to 0 plus m. So there's that. Now what? What's the time? Oh, I should get on. 1 times m is m. It's really annoying that I can't use the simplifier. I need to use induction for this, surely. Yes. Oh wait. Let's rewrite 1x suck 0. Let's just see what's going on. Do I need to use induction? Have I got suck mul? Oh, I haven't got suck mul yet. That's a shame. Okay, so induction m with DHD. There, and this will be true by definition, right? Let's just see what happened then. The base case was to prove that suck 0 times 0 is 0, and you just keep unfolding things, and it's true by definition. If you want to prove that two numerals are the same, it's always true by definition. Now, what do we have here? This is going to rewrite mul suck. Oh yeah, I finally sorted out my audio issues. And then I rewrite HD, I guess. Yeah, that's what's stopping me prove things. But now I bet that's true. And now surely that's true by definition. It is. And so that line can go. And now I want my tick. Thank you very much. Mul add. Yeah, I'm sorry, Kitster. Mul add. Oh, yeah, I see. Distributivity. I need to prove it by induction on something. I'm really concerned. I don't have suck mul. Why haven't I proved suck mul yet? Suck mul looks really important. If I had suck mul, no, Kitster is, and that's short for cat. That's a generic word for a cat, isn't it? My cat is called Squidgy Gravity Epcirc III. Squidgy Gravity Epcirc Buzzard III, because we got her just after I got an Epcirc grant. But everyone just calls her Kitty, or Gravity, which was my daughter's name for her when she was like 4. My cat is called Gravity. I'm going to do induction on. I think induction on T is doomed to failure. Induction B with DHD. Right, let's see if I can get through this stuff quickly. So this might be true by definition. Let's try. Is it true by definition? It is. And now this one here. Let's try simp add suck. It's really annoying that simp doesn't know that. Let's see how far we get. Let's just keep adding things to the simplifier. How close are we? Mul suck. Have we got mul? Mul suck is the one we have. Oh, is it awkward doing maths when maths is broken? Mul suck we have. I'm just going to feed more. Oh, HD we certainly need. HD. Has that done it? There we go. So there we go. You see, you don't have to do all these rewrites. The simplifier can fathom it all out for you. Ah, mul a sock, and I've still never done suck mul. And we're going to do suck mul. Is that a thing? Because we don't have suck mul yet, so I think I've forced an induction on C. Induction C with DHD. And now this one here, that will just be lots and lots of applications of mul 0. So that will be refl. There. And now here in the successor case, so let's do simp mul suck and the inductive hypothesis. I bet this will do it, won't it? No. Oh, what do I? My problem is, so what do I need to know? A plus B times yada yada yada. I think I need. I think I know. I need to know mul add. Mul add. Let's throw in mul add with the correct number of D's, and there we go. No goals, but no tick either. Where's the tick? There's the tick. Finally, suck mul. I've been waiting for you, suck mul. That's not going to be true by definition because mul suck is true by definition. So I'm going to do induction on B, I suppose. Induction B with DHD. The base case is hopefully true by definition. It is. And the inductive step, what am I going to use? So simp HD, that's a good place to start, isn't it? Because we're certainly going to use HD, and we can already do that rewrite. What's the story now? Suck A times suck D is suck D plus A times suck D. That's kind of annoying. Oh, if I knew that suck A, I suppose I could use suck ek add. If I got suck ek add 1, that might be useful at this point. Is that a thing? Oh, I've put a full stop instead of a comma. Suck ek add 1. That is a thing. Oh no, it's rewritten it everywhere. Oh, great. So this has got quite chaotic. So who knows? I mean, this is going quite badly, actually. I'm not entirely sure I'm going to be able to do this one. But the point is, I need to use mul add. Now, how am I doing? Is this even close to being true? Do I have? I don't have add mul. This is going really badly. I think I better start. I think using the simplifier was a bad move. Or maybe I'm supposed to do induction on A. Let's try this. Let's rewrite mul suck. I think I've bitten off more than I could chew here. Let's go out to the normal way. Suck A times D. Let's rewrite mul suck again. Now how am I doing? And suck mul is what I'm trying to prove. So now I can rewrite HD. And now what have I got? Ah, now this looks... And now... what does the simplifier do with this? How far does it get me? No, okay, so I'm going to have to use add right com. Okay, so I've finally actually read the... I've read the hint. And add right com does what for me? It didn't go at all. Add right com is kind of... What? Add right com looks perfect. Oh, maybe I need add suck. Rewrite add. What about? This is horrible. What evil lemma? What? Oh, what? What? No. Oh, I see. Oh, how annoying. Maybe I need to rewrite add a sock. Oh, jeez. And there was me thinking it was all going to be easy. I should have rehearsed. And now, oh, that's failed. Oh, I rewrite add a sock in the correct direction. And now I can do rewrite add suck finally. And now I wonder whether, am I close? What does congra do? Oh, this looks better. Oh no, these are goals that aren't true. I don't need add right com. I think I'm going to use. Maybe now is the time to do. Maybe now is the time to do suck egg add 1. Oh, fabulous! I can't prove suck mul. There was me moaning that we didn't have suck mul. And now can I do it again? And now I'm hoping that I can solve. Now maybe simp will do this. Oh, thank goodness for that. There you go. That was an interesting level. And there's me laughing at undergraduates when they say they're stuck. And finally, here's add mul. And now this one is surely going to be induction on T. Induction T with DHD. And the first case will be true by REFL. What's the first goal? The first goal is all about 0 equals 0. The first goal is true by REFL. And now I've got to prove this. So my guess is I use mul suck. I've got to be careful here, haven't I? Have I? No, let's try. No, maybe I'm okay. Mul suck. Let's go back to the cheating method. Simp mul suck an HD. How far did we get with that? Oh, there you go. It does it. Great. That'll do. Yay. Go for, yeah, good old cheat method. Now what? Mulcom. And that's induction. Induction. I could do either of them, couldn't I? Induction, I don't know, A with DHD. Let's do induction on A for a change. A doesn't get much love. And the base case, I'm going to use simp, which is 0. Which one is true by definition? If I tell the simplifier about 0 mul, that should do the base case. Did it? It did. So there's the base case in its nice little brackets because I had 2 goals. And now let's do simp something. Let's just try that for a start. Let's try just running the simplifier. So what does it need to know? Suck mul. And mul suck. Oh, I see. That's why I've just proved these things. What happens after that? And I'll tell it HD as well. Tell it the inductive hypothesis. HD. This might do it. It does do it. So there's that. And now finally mul left com. Reread the dots to rewrite so you know all the tricks. Oh, I see. Mul left com, we can prove this by rewriting, can't we? Rewrite mul sock this way. Yeah, I'm sorry, Kitster. And now I can rewrite mulcom AB to ensure that we do the right one. So now I'm good, right? Rewrite mulsock. And now this is mulsock isn't true by, so now that's true by REFL. Look, I can do, this is another trick. I can do rewrite assumption. I didn't hack there. RWA tactic is rewrite then assumption. And I hacked the rewrite tactic so that it didn't try REFL at the end of everything, but I didn't hack RWA. And so RWA tries rewrite at the end and rewrite works. So that's the end of multiplication world. Oh no, it isn't the end of multiplication world. I must have forgotten. Have I missed a tick? Where's the tick? Oh man, the very first one. Come on. Go on, proof complete. You know you want to give me that tick. Oh yeah, finally. Great. So now I'm finally into Power World. So all these levels were written by Sean Carey, who was just this random person that randomly came along from Leeds and said, I want to do some lead. And I was like, great, help make my game. So here's Power World. 0 to the power 0 is 1. That's true by definition. There's my tick. 0 to the power suck m is, I don't even know what's true by, I don't even know how this works. So this, I wonder if this is true by definition. Let's try REFL. It is, it's true by definition. There you go. This is definitional equality great. Proof complete. A to the power 1 is A. So what's the definition of what? Let's see if this is true by definition. No, it's not. So let's figure out what's going on here. So we can rewrite 1x suck 0. There, that's true by definition. And now I can rewrite pow suck. There, that's true by definition. And rewrite pow 0. That's true by definition. Ah! It's 1 mul. Do we have that? Rewrite 1. I suppose we could keep going. Rewrite 1x suck 0. Let's keep going. There. And now what? I think mull suck is the thing that's true by definition. Yeah, I've run out of steam now. Do we have this lemma? Do we have one mull? Did I cunningly prove it? Yeah, one mull we have. So this is exact one mull A. That should prove that. It does. And now I can delete all those because they're true by definition. So there you go. The proof that a to the power 1 is A is one mull A. Isn't life great? Now what? 1 to the power m is 1. Oh, I see. We don't have any lemmas about raising things to a general power m. So this one we definitely have to do by induction. Induction m with DHD. And now the first goal is true by definition. And now this one, let's try simp pow suck and HD. You see, I should have been training the simplifier. Yeah, you see, it's done it. If I've been training the simplifier all the way along, then these things would be much easier. And now what? Pow add. Oh, hell's bells. I'm going to do that by induction on. I don't have. Yeah. I think I'm going to do it by induction on n. I think anything else is too risky. I mean, induction on a won't work. I mean, it won't even work in mathematics. An induction on m might work with DHD. How am I doing? The first goal, maybe that's true by REFL. It's not. Oh, so even the base case, we have to prove something. Hell's bells. Simp. Let's see what the simplifier makes of it. Oh, I see. It doesn't know pow 0. Pow 0. Let's try that. And it probably won't know mull 1 either. Oh no, it's done it. So that the first goal was solved. And now the second goal. I see. We need to use pow suck somehow. So we maybe rewrite, kind of add suck that way or something. Is that a thing? Oh, it didn't work. Oh no, sorry, rewrite add suck the normal way. There. And now simp pow suck. How far will that get us? Oh, and we also need it to know about HD, of course. And, oh, bingo, it's done it. Right, 3 levels to go. Mull pow. That's going to be induction on n, isn't it? Induction on everything else wouldn't even work in maths with DHD. And the first goal is probably true by definition. It is. And the second goal, rewrite pow. Let's simp pow suck and the inductive hypothesis. How far will that get us? That gets us as far as everywhere. So there's that. And finally, oh no, the last but one. Boss level is pow pow. Yeah, so this is okay. So at the bottom here we have this interesting comment, right? What happened at the end of all the other worlds is that when you somehow finished proving every fact about addition on the natural numbers, you've proved that addition is an additive monoid. And when you finish proving every fact about multiplication on the natural numbers, including the relationship between multiplication and addition, you've proved that the natural numbers are like a commutative semi-ring. But when you finish proving every single level about powers, then you haven't proved anything. It's kind of annoying. I don't quite know the answer to that question. We should have proved that the natural numbers are something, but apparently we haven't. Maybe that's because there's no other thing which satisfies these lemmas apart from the natural numbers or something. Because I'm not sure like 0 to the power -1 doesn't make sense. So maybe the non-negative reals. Is it? Is this true for the non-negative reals? I suspect it might be. Anyway, let's do induction with DHD. And now hopefully the base case is true by definition. It is. And the I'll put it in brackets for any computer scientists watching. In this case, simp pow suck. Pow suck. Oh, and HD, of course. Have we used? And now, so we need HD as well. And now what else do we need? We need, maybe we need mulsuck. And now we need, and now we need pow add, and we've proved that already. You see, isn't this an incredibly well put together game? There we go, done. There. And now there's this dumb trick. There's this dumb trick for proving this one, is that I can probably use ring. So maybe not quite yet. Yeah, it doesn't know. Here, let's just copy this. Now what have I got? If I rewrite power 0, I want to get rid of all the rings. I see that ring tactic doesn't know about powers. I need to remove all of the powers. So now this goal here. Oh, the ring tactic doesn't know about suck either. What about repeat, rewrite, suck ek add 1. I think we need to get rid of the sucks. There we go. And so now our goal is now something which is true in all commutative rings. So the ring tactic should do this. And it does. So there we go. And that's the end of the natural number game. Oh, and that's the cheat. Does that link still work, I wonder? Is that a thing? There you go. Repeat rewrite power 0 ring. Apparently I didn't need that line there. Is that true? Ring, does that work? Well, it must work. It does work. I have no errors. Blah, 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 blah. So there you go. Proof complete. And look at that. Do you know what? I've never seen the natural number game look like that before, because I played it all through once before Mohammed had put in these fancy green and blue. It looks kind of cool, doesn't it? Oh, there you go. Yeah, that looks really nice. I'm going to make them all, as you see, I haven't made them all green yet, right? I should probably make them all green. That would be nice to do. But I'm done. I'm now going to go over to, where am I going to go? I'm going to go to that. I'm going to go to that, that Discord. Discord, that's what it's called. Let's go to Discord. And so, let me copy the link into the chat. I'm gonna, oh shoot, you're absolutely right. I'm gonna feed the cat and then I'm gonna go to the Discord. Right, I'm gone. Thanks for watching. Cheers. Mehmet learned something, which is great. Yeah, definitional equality, not taught in maths departments. And I'll stop. What will I do? I'm gonna, I see.